Hi, everybody. I'm going to do a quick presentation here where I'm going to review stoichiometry with you with one problem, and then show you how you deal with finding the volume of a gas at STP that's involved in a chemical reaction using stoichiometry. So let's review from yesterday. Remember that to use equation for stoichiometry, that equation needs to be balanced. So go ahead and do that. Work on getting the coefficients that go in front of here. I'll give you just a second to do that. You can pause the presentation and come back if you need a little extra time. So to balance this reaction, I noticed that the aluminum's by itself, so I'm going to just let that till last. I'm going to start with the oxygen this time. And I have 3 on one side, 2 on the other. Least common multiple is 6. So I'm going to put a 2 right here so that I have 6 oxygen on the right. I'm going to put a 3 right here so that I have 6 oxygen on the left. That gives me 4 aluminum. So I'm going to put a 4 in the front of there. And my coefficients for this balanced reaction are 4, 3, 2. Now remember, those coefficients can represent individual atoms, molecules, and formula units, or they can represent moles of each substance. So using them in the mole format, I could answer a question like this. Calculate the mass of aluminum, that would be this one, needed to produce 0.350 moles aluminum oxide. So we know how much aluminum oxide we have, and we need to figure out how many grams of aluminum are needed. Remember, always start with the number you're given, 0.350 moles of the aluminum oxide. Set up a factor label. The unit on the bottom, the unit on the bottom has to match so that it will divide out. And I can use the mole ratio 2 to 4 to convert to moles of aluminum. Now, if this problem said calculate the moles of aluminum, I would be done, but it says to find the mass. So I need one more step to go from moles of aluminum to grams of aluminum. And looking at my periodic table, it is 26.98 grams per mole. So the moles aluminum oxide divides out, the moles aluminum divides out. I will multiply by 4, divide by 2, and multiply by 26.98. And I got 18.9. I'm keeping 3 sig figs. The 0 counts because it is trailing and there is a decimal. And my label is grams of aluminum. So now I would know exactly how much aluminum is needed to produce that same amount of aluminum oxide. But what about the oxygen? The oxygen being a gas, we don't normally measure gases by their mass in the lab. What we generally do is we often determine the volume of a gas that is either used or produced. And to do that, we're going to need a new piece of information called the molar volume of a gas, so that we can now add that in as another thing we are able to use in our stoichiometry problems. We're also going to practice other units then, units of volume like liters, milliliters, centimeters cubed. And we're going to continue to use proper sig figs and add labels on our answers. So what is the molar volume of a gas? Well, this goes back to Avogadro's work, where, remember the Avogadro's principle that a mole of any substance contains 6.022 times 10 to the 23rd particles. So it was determined that that many particles of gas at STP, this means standard, I could spell standard, temperature and pressure. Now, later we'll worry about those exact units, but standard temperature is 0 degrees Celsius. Standard pressure is as you would know, it may be in pounds per square inch, 14.7 pounds per square inch. In the metric units and other units that we use more in chemistry, it has other values such as 1 atmosphere or 760 millimeters mercury or 101.325 kilopascals. We'll deal with the exact numbers later, but what you need to know is that if conditions are at STP, that 1 mole of any gas is going to occupy 22.4 liters. Now, when it says any gas, that means any gas. It can be an element, like neon. It could be a compound, like carbon dioxide. It could even be a mixture, like air. 1 mole of any gas is going to occupy 22.4 liters of space, okay? Now that this relationship is established, this gives us another relationship equality that we can use in our factor label problems. So I'm going to do 2 samples using it, and then you'll be able to apply it to your homework. So for example, here's the equation that we already balanced. What if we have 10 grams of aluminum to react? How much oxygen do we need to react with that? Do we have enough oxygen in the stockroom? That's, a question that I might answer. What size tank do I need to get? At what pressure? Well, obviously, we're doing this at STP. We'll deal later with other pressures and other temperatures. When I say later, I don't mean in this unit. I mean in our gas law unit. But you do this problem the same as we've been. You start with the number that you're given, and then you start setting up a factor. Remember that if it's in any unit other than moles, your first job is to convert it into moles. So 26.98 grams of aluminum is a mole of aluminum. Okay. Next, you do the mole to mole ratio to relate one substance to the other. We want to get rid of the moles of aluminum, and we're trying to calculate something about the oxygen. So we'll switch from aluminum to oxygen using the 4:3 relationship. Now, at this point, we have to really look closely at what does the question ask. If it said determine the moles of oxygen, we're done. If it said determine the mass of oxygen, then we would have a step to go from moles of oxygen to grams of oxygen, because that's a mass unit. But this isn't what it says. This one says determine the volume of oxygen. So we need a step where we can convert from moles of oxygen to liters. Since it is at STP, we know that 1 mole of any gas, and oxygen is a gas, and you know that because of the little subscript G standing for gas, occupies 22.4 liters of space. We have now set up our stoichiometry where our units divide out, and we are left with the unit we're looking for, the liters of oxygen. We would divide by the mass times 3/4, multiply by 22.4, and in the end, with 3 sig figs, because our starting number has 3 sig figs, those zeros count because of the decimal, we would get 6.23 liters of oxygen. If we needed to convert that into milliliters or centimeters cubed, we could do so using metric conversions that we learned earlier in the year. So what about the other way? What if you start with the volume? Like, look at this problem. Again, the same balanced reaction. What mass of aluminum oxide will be produced by the reaction of 750 milliliters of oxygen gas? Now, it says here there's plenty of aluminum, okay? So we start with our 750 milliliters of the oxygen. Now, we need to convert that to liters so that we can use the molar volume. So my first step is going to be that metric conversion. We know that a milliliter is 1/1000th of a liter. So I'm going to multiply by 0.001. My next step then, remember, if I start with anything other than moles, I want to try and get it into moles, is going to be to use the molar volume of the oxygen. Okay, so I've used the molar oxygen volume of the oxygen. And if you go back and you look at your units, Milliliters divides out, the liters divides out. Now I have moles of oxygen. Once I have moles of oxygen, I can relate the oxygen to the other substance. In this question, we're trying to find some information about the aluminum oxide. So I'm going to put my moles of oxygen on the bottom and moles of aluminum oxide on the top. Filling that in, we see it's a 3-to-2 relationship. Now, if this question said how many moles of aluminum oxide, I'd be done. But it says what mass, so I need another step. I previously added up the molar mass of aluminum oxide. It is 101.96 grams in every mole of aluminum oxide. Again, going back and examining my units, I set it up right because my moles of oxygen divide out, my moles of aluminum oxide divide out. So I have to take 750 times 0.001, divide by the 22.4, times by 2, divide by 3, times by 101.96. This time, if you look back here, my number that I started with only has 2 sig figs. This trailing 0 doesn't count because there's not a decimal anywhere. Remember, for a trailing 0 to count, there has to be a decimal somewhere. So this is only 2 sig figs, so I'm going to take my answer. I'm going to round it to 2 sig figs and make sure that I have a label. So you can use this conversion either way, like to find volume, or you can use it to convert volume into moles, as long as it's a gas. You cannot use it for solids, liquids, or aqueous solutions. It is only good if the substance is a gas and the reaction is at STP. And I see that I did not put that one in here. I forget to put that in any of the problems. For right now, assume that our reactions are at STP. Eventually, like I said, we're going to study gas laws, and we will learn how to adjust those numbers for other pressures and other temperatures, because pressure and temperature greatly affect the volume that is occupied by a mole of gas. So good luck with your homework. If you have any questions, please don't hesitate to ask.